What if the story of your life, the one you remember with such unshakable certainty, is not written in ink? What if the past is not a fixed and monolithic statue, a memorial to what has been, but is instead a fluid sculpture of possibilities, only solidifying into its final form when observed from the form present? It's a notion that feels like a violation, an affront to the most fundamental law of our existence, the relentless one-way arrow of time. We believe with every fibre of our being that yesterday is gone forever. It is a sealed room, a finished chapter, a country to which we can never return. The decisions we made, the paths we took, the moments of triumph and regret, they are all locked away in the immutable vault of history. The cause always precedes the effect. The stone is thrown, and only then does the ripple spread. This is the bedrock of our sanity, the scaffolding upon which we build our understanding of the universe. But what if that bedrock is merely an illusion, a comfortable assumption we've made based on our limited macroscopic perspective? What if, on a level so fundamental, it underpins all of existence, the universe operates by a set of rules, so bizarre, so completely alien to our intuition that it allows for an effect to seemingly reach back in time and define its own cause? This isn't a question of philosophy, nor a fanciful premise for science fiction. It is a profound and deeply unsettling question that emerges from the very heart of modern physics, a domain where the solid ground of classical certainty dissolves into a shimmering mist of probability. Welcome to the quantum realm. Down here in the subatomic world of electrons, photons, and the fundamental constituents of reality, the familiar rules of our world are not just bent, they are shattered. This is a place where particles can exist in multiple places at once, a ghostly superposition of all their potential states. They can tunnel through impenetrable barriers as if they were smoke, and they can be linked across vast cosmic distances by a mysterious connection Einstein famously derided as spooky action at a distance. But of all the bizarre behaviors exhibited in this quantum wonderland, one stands out as the most challenging, the most reality-bending, and the most consequential for our understanding of time itself. It is a phenomenon that suggests the very act of observation, the simple process of looking at something to find out what it is not a passive act of discovery. Instead, it is a profoundly creative act, a moment where we, the observers, force the universe to make a choice, to collapse an ocean of possibilities into a single concrete reality. The story of this revelation, this deep cosmic secret, begins with a deceptively simple piece of equipment, a barrier with two thin parallel slits cut into it. This is the stage for the most famous and arguably the most important experiment in the history of science, the double-slit experiment. Imagine firing tiny indivisible pellets like microscopic marbles at this barrier. Some will be blocked while others will pass through one slit or the other, striking a detector screen behind. The result is precisely what you'd expect. Two distinct bands on the screen, a clear record of the pellets that went through the left slit and the pellets that went through the right. It is simple, logical, and intuitive. Now let us change the projectile. Instead of marbles, we will fire particles of light photons one at a time. A photon is a quantum object, the smallest possible packet of light energy. Firing them one by one ensures they cannot possibly interact with each other. If a photon is a particle, a tiny bullet of light, then we should expect the exact same result as before, two distinct bands on the detector screen. But that is not what happens. Instead, something extraordinary, something impossible begins to emerge. As the photons build up on the screen one by one, they do not form two simple bands. They create a complex pattern of many alternating bright and dark stripes, a pattern known as an interference pattern. This is the unmistakable signature not of a particle but of a wave. It's the same pattern you would see if you dropped two stones into a pond. The ripples from each stone would spread out, meet, and interfere with each other. Where the crest of one wave meets the crest of another, they reinforce, creating a larger wave. Where a crest meets a trough, they cancel each other out, leaving the water still. The interference pattern on our detector screen tells us unequivocally that the light has behaved like a wave. But how can this be? We are firing single photons. Each individual photon traveling alone must have somehow passed through times. Both times slits simultaneously interfered with itself, and then struck the screen at a precise location dictated by this self-interference. The single photon in this moment is not a particle at all. It is a wave of pure potential, a ghost of possibility that explores every available path at once. This is the core mystery of quantum mechanics' wave-particle duality. Every fundamental entity in the universe seems to possess this schizophrenic nature, behaving like a well-defined particle when you look at it one way and a spread-out ethereal wave when you look at it another. The strangeness, however, is about to deepen immeasurably. Bewildered by this result, physicists naturally ask the obvious question: which slit did each photon times actually go through? To find out, they placed a detector at the slits, a tiny sophisticated gatekeeper capable of recording which path each photon took on its journey. The logic is flawless. By observing the photons at the slits, we can finally solve the mystery and discover how a single particle can create a wave pattern. The experiment is run again, photons fired one by one. The detectors at the slits work perfectly dutifully, reporting that each photon passes through either the left slit or the right slit, but never both. The mystery, it seems, is solved. The photons are particles after all, taking one definite path. But then we look at the detector screen at the back, and the interference pattern, that ghostly fingerprint of the wave, is gone. In its place are just two simple bands, exactly like the ones produced by the microscopic marbles. The very act of watching, of asking the question, which path did you take, has profoundly altered the outcome. It is as if the photon, aware of being observed at the slits, instantly abandoned its wave-like multipath exploring behavior and was forced to commit to choose a single definite path, behaving like a simple particle. The universe, it seems, will show you a wave, or it will show you a particle, but it refuses to show you both at the same time. The act of measurement is not a gentle inquiry, it is a command. It forces the shimmering, uncertain quantum world to collapse into the solid, definite classical world we experience. For decades, this observer effect remained one of the most profound and unsettling pillars of physics. It suggested a participatory universe, one in which reality is not a pre-existing movie we are merely watching, but a dynamic script we are co-authoring with every observation we make. And it was here, at this dizzying precipice of understanding, that one of the 20th century's greatest minds, the American physicist John Archibald Wheeler, stepped forward to ask a question so audacious, so contrary to common sense, that it would push the boundaries of reality itself. Wheeler was a true titan of physics, a collaborator of Einstein, and a mentor to generations of brilliant scientists. He was a man who reveled in the deepest cosmic questions, coining terms like black hole and wormhole. He was not one to shy away from the radical implications of quantum theory. He looked at the double-slit experiment, at this strange duality, where a particle's nature depends on how you measure it, and he conceived of a truly diabolical twist. The standard experiment involves a choice made times before times. The photon reaches the slits. Either you place a detector there to see which path it takes, or you don't. The photon's subsequent behavior, particle or wave, depends on that prior setup. But Wheeler wondered, what if we could wait? What if we could let the photon pass the slits when it must have already somehow made its decision to travel as a particle through one slit, or as a wave through both and only times, then asterisk? Decide which question to ask. What if we could delay our choice of measurement until the very last moment, an infinitesimal fraction of a second before the photon hits the final detector? This is the genesis of the delayed choice experiment. Imagine our double-slit setup, but with a crucial modification. The final screen is not fixed, it is retractable. We fire a single photon. It leaves the emitter, travels towards the two slits, and passes through. In this moment, according to our classical intuition, its history is set. It has either travelled through the left slit, the right slit, or in its strange quantum wave state through both simultaneously. Its past is for all intents and purposes already written. The photon continues its journey toward the back wall. Now, in the final nanosecond just before it would strike the detector, we make our choice. If we want to know which path it took, we quickly remove the screen. Behind where the screen was, we have placed two powerful telescopes, each one aimed precisely at one of the slits. If the photon arrives at the left side telescope, we know it came through the left slit. If it arrives at the right side telescope, we know it came through the right slit. By removing the screen and using the telescopes, we are asking the which path question. We are forcing a particle-like measurement. And in this scenario, Wheeler predicted the photon will be detected by one telescope or the other, confirming it behaved like a particle and took a single, definite path. But what if we make a different choice in that final nanosecond? What if we decide to leave the screen in place? The screen, by its very nature, does not record which path the photon came from. It simply records where it lands. Because it erases the which path information, it allows the wave-like nature to manifest. By choosing to leave the screen in, we are asking the wave question. We are choosing to observe the interference pattern. And in this case, Wheeler predicted the photon, whose path past the slits is already a matter of history, will contribute to the formation of an interference pattern, proving it must have behaved like a wave and travelled through, * both time slits at once. Consider the staggering implication. The choice we make in the present to insert or remove the screen appears to determine the reality of what the photon did in the past. If we choose to look for the particle, it will have behaved like a particle. If we choose to look for the wave, it will have behaved like a wave. Our present action seems to be retroactively shaping a past event. It's as if you could stand at the finish line of a race, and by choosing which camera to look at, determine whether a runner had stayed in a single lane for the entire race or had somehow run in 2 lanes at once. To make his point even more dramatic, Wheeler scaled his thought experiment up to an almost unimaginable cosmic scale. He asked us to imagine a distant quasar, a phenomenally bright galactic core billions of light years away. The light from this quasar travels across the universe towards Earth. On its journey, it encounters a massive galaxy, a colossal celestial body whose immense gravity acts like a lens, a gravitational lens bending space-time itself. This cosmic lens can split the light from the quasar, creating 2 distinct paths for it to reach us. A photon leaving that quasar 5 billion years ago embarked on this epic journey. It travelled for eons across the expanding void of intergalactic space. When it reached the gravitational lens 1 billion years after it started, it faced a choice. Did it travel along the path to the left of the lensing galaxy? Or did it travel along the path to the right? Or did it, as a quantum wave, travel along both times, paths simultaneously? After traversing one of these paths, or both for another 4 billion years, that ancient photon finally arrives, at Earth, at the telescope of an astronomer. And here in the present day, that astronomer has a choice, the same delayed choice as in the laboratory. They can configure their telescope in one of 2 ways. They can use a setup that focuses on the 2 distinct arrival points, effectively looking to see which of the 2 paths the photon took to get here. If they do this, they are asking the which path question. In this case, they will always find that the photon arrived from either the left path or the right path. This present-day measurement seems to force the photon to have chosen a single, definite route 1 billion years after it left the quasar. But the astronomer can make a different choice. In the final picosecond before detection, they can insert a beam splitter, a device that recombines the light from both paths. This arrangement effectively erases the which path information. It is the cosmic equivalent of leaving the screen in place. It asks the wave question, looking for the telltale signs of interference between the 2 paths. And if they do this, they will find an interference pattern proving that the single photon must have travelled along both times, paths, simultaneously across billions of light years of space. A choice made in a laboratory on Earth today appears to define the history of a photon that began its journey before our planet had even formed. The past in Wheeler's vision is not fixed. It is an open question. It is a great smoky dragon, as he poetically described it. Its tail, the emission from the quasar, is known. Its mouth, the detection at the telescope, is known. But its body, the vast journey in between, remains a shimmering, undefined cloud of possibility until a measurement is made. The act of observation in the present does not discover the past. It participates in the creation times of the past. For years, this was a mind-bending thought experiment, a theoretical puzzle designed to probe the absolute limits of quantum logic. It felt like a paradox, a piece of metaphysical trickery that couldn't possibly map onto the real world. But physics is not philosophy. Its ideas, no matter how wild, must ultimately be tested. Could such a thing be true? Could an action today truly reach back through the corridors of time and change what has already been? The answer discovered in laboratories here on Earth would prove to be even more astonishing than Wheeler himself could have ever imagined. It would confirm that the universe is indeed a far stranger, more mysterious, and more deeply interconnected place than we ever dared to believe. The granite of yesterday we are now forced to consider might just be clay in the hands of tomorrow. What if the past is not as solid as you remember it? What if every history book, every memory, every fossilized bone is merely the most recent draft of a story that is still being written? A story whose ending can retroactively change its own. Beginning, this is a thought that feels like a violation, a trespass against the most fundamental law we know, that cause must always precede effect. The arrow of time, we believe, flies only in one direction, from a fixed and immutable past toward an open and uncertain future. But a revolution in physics born from a quiet collision of ideas would eventually force us to question this deepest of all intuitions, suggesting that the universe might be a far more unsettling and far more participatory place than we could ever have imagined. To understand this profound rupture in our concept of reality, we must first return to a simpler, more elegant time. A time when the cosmos was seen as a grand and predictable machine, a celestial clockwork set in motion by a divine watchmaker operating on principles of absolute certainty. This was the universe of Isaac Newton, a reality built from two distinct and entirely separate ingredients, particles and waves. Particles were the solid stuff of existence. They were like infinitesimal billiard balls, hard, discrete, and localized. A particle is times here, times, or it is times there, asterisk. It cannot be in two places at once. It follows a clear, predictable trajectory through space. Everything you can touch, from the stone beneath your feet to the distant glittering stars, was thought to be composed of them. Waves, on the other hand, were entirely different creatures. A wave is not a thing but a disturbance, a vibration. It is a pattern of energy moving through a medium. Think of the ripples spreading from a pebble dropped in a still pond, or the sound of a voice travelling as compressions through the air. A wave is diffuse, spread out, and defined by its properties, its frequency, its amplitude, its ability to interfere with itself. When two waves meet, they don't collide like billiard balls. They overlap, creating a new, more complex pattern. Where their crests align, they amplify each other. Where a crest meets a trough, they cancel each other out. This beautiful dance of reinforcement and cancellation is called interference, and it was considered the unmistakable signature of a wave. For centuries, these two categories were the unshakable pillars of physics. Particles were particles, and waves were waves. The universe was neat, it was orderly, and everything had its place. Into this tidy world, the question of light had long been a stubborn puzzle. Newton himself had championed the idea that light was a stream of particles or corpuscles, tiny bullets of energy travelling in straight lines. This explained why objects cast sharp shadows, why light seemed to reflect like a ball bouncing off a wall. But others, like the Dutch scientist Christiaan Huygens, argued passionately that light must be a wave. The debate raged for over a century, a fundamental disagreement about the nature of the very medium that illuminates our world. The stalemate was finally and decisively broken in 1801 by an English polymath of breathtaking genius, Thomas Young. He devised an experiment of such simple elegance that it seemed to settle the question for all time. It is an experiment whose echoes will haunt us throughout our journey. It is called the double-slit experiment. Imagine a barrier with two thin parallel slits cut into it. If you were to fire solid objects, say grains of sand, at this barrier, you would expect to find two distinct piles of sand forming on the detector screen behind it, each one aligned with a slit. This is the behavior of particles. Simple, direct, predictable. Young, however, did this with a beam of light. He shone light onto the barrier and observed the pattern it created on the screen behind. What he saw was not two simple bands of light. Instead, he saw a beautiful, intricate series of bright and dark bands, a shimmering tapestry of light and shadow. This was the smoking gun. This was an interference pattern. It was the unambiguous signature of a wave. For this pattern to form, the light must have passed through times. Both times slit simultaneously like a wave on the surface of a pond. The wavelets emerging from each slit then interfered with each other, amplifying in some places to create the bright bands and cancelling out in others to create the dark ones. A particle could never do this. A particle must choose one slit or the other. The conclusion was inescapable, and it was celebrated as a triumph of reason. Light, the great mystery, was definitively a wave. The clockwork universe remained intact, its laws confirmed. Physics, it seemed, was well on its way to being solved, but the universe, it turns out, is a far more mischievous storyteller. The dawn of the 20th century saw the polished facade of classical physics begin to crack under the weight of strange new observations. Phenomena like blackbody radiation and the photoelectric effect simply refused to conform to the established wave theory of light. When light was shone on certain metals, it would kick out electrons, but only if the light had a high enough frequency, a certain color. Making the light brighter, which meant a more powerful wave, did nothing if the color wasn't right. It was as if the energy wasn't being delivered in a continuous flow, but in discrete, concentrated packets. It was a young patent clerk in Bern, Switzerland, who dared to voice the heresy that would unravel everything. In 1905, the same year, he revolutionized our understanding of space and time. Albert Einstein proposed a radical idea. He suggested that we must resurrect Newton's abandoned concept. Perhaps light was not a continuous wave after all. Perhaps it was composed of tiny discrete packets of energy, indivisible bullets of light he called quanta. Later, they would be given a new name, photons. This perfectly explained the photoelectric effect. One photon hits one electron, transferring its energy like a cue ball. If the photon doesn't have enough energy on its own, nothing happens no matter how many of them you send. It was a brilliant solution, but it created an impossible contradiction. Thomas Young's experiment had proved beyond any doubt that light was a wave. Einstein's theory now demanded that it be a particle. How could it be both? How could one single entity be a localized bullet-like particle and a spread-out ethereal wave at the very same time? It was a paradox that cut to the very heart of reality itself. This schism in the nature of light was only the beginning. The rabbit hole was about to get much, much deeper. A young French aristocrat, Prince Louis de Broglie, pondering the universe's love of symmetry, made a conceptual leap of such staggering boldness it bordered on the mystical. If waves like light could sometimes behave like particles, he reasoned, then perhaps particles, the very building blocks of matter, like electrons, could sometimes behave like waves. The idea was so bizarre that his doctoral advisors were skeptical until they showed his thesis to Einstein, who saw its deep, resonant truth. Suddenly, the paradox was no longer confined to the strange nature of light. It had infected the entire material world. You, the chair, you're sitting on the air, you breathe the distant moon. Everything, according to de Broglie, had a wave-like nature. This was not a metaphor, it was a physical prediction. An electron was not just a tiny spinning ball of charge. It was also somehow a diffuse wave of potential, a ripple in the quantum field. The implications were mind-bending. The solid, dependable world of classical physics was dissolving into a ghostly realm of probabilities and phantoms. And so the stage was set for the ultimate confrontation, the experiment that would become the foundational mystery of the quantum age. Scientists decided to perform Young's double-slit experiment again, but this time with the particles that de Broglie had imbued with wave-like properties, electrons. They developed a source that could fire a single electron at a time. This was crucial. By sending them one by one, there was no possibility of electrons interacting or interfering with each other. Each electron would make its journey alone. We can envision this in our minds. An electron, a single indivisible particle, leaves the emitter. It flies toward the barrier with its two slits. Like a tiny bullet, it must make a choice. It must pass through the left slit, or it must pass through the right slit. There is no other option. After it passes through, it strikes a detector screen behind the barrier, making a single tiny dot of light recording its final position. We wait. We fire another electron. It too travels its path, makes its choice, and leaves another dot on the screen. We do this for hours, firing thousands upon thousands of electrons, one after another after another. What pattern do you expect to see on the screen? Common sense screams the answer. We are firing particles. We should get the particle pattern. Two distinct bands of dots, each one aligned with one of the slits. But that is not what happens. As the dots accumulate on the screen, a ghostly and impossible pattern begins to emerge from the noise, a series of bright and dark bands, an interference pattern, the unmistakable, undeniable signature of a wave. Let the sheer, bone-chilling impossibility of that sink in. We sent single particles one at a time, yet we got a pattern that could only be created if each electron had passed through times both slits simultaneously times and interfered with itself. The single, indivisible electron had somehow been in two places at once. It was a phantom, a wave of pure potential that explored every possible path before coalescing into a single dot on the screen. It was as if reality itself was refusing to commit, holding all possibilities in a shimmering, ghostly superposition. This result was so deeply unsettling, so contrary to all logic, that physicists felt compelled to challenge it to expose the trick. They reasoned the electron must be going through one slit or the other. We just don't know which one. The only way to solve this is to watch it. So they modified the experiment. They placed a delicate measuring device, a tiny detector, at the slits themselves. This detector would be able to tell us for each individual electron which path it actually took. Did it go through the left slit, or did it go through the right? It was a simple question, and now we would have a simple answer. The experiment begins again. We fire one electron. It flies toward the barrier. Our detector flashes. Left slit, it tells us. The electron then continues on its journey and hits the screen, making a dot. We fire another. The detector reports right slit. Another dot appears. We fire a third. Left slit, a third dot. We repeat this process thousands upon thousands of times, meticulously recording the path of every single electron. We have our answer. We know which slit each one went through. Now we look at the final pattern on the screen behind the barrier, expecting to finally understand what's happening. But what we see is even more shocking. The interference pattern is gone, completely vanished. In its place are two simple, distinct bands, exactly where we would expect them to be if we were just firing tiny bullets. The particle pattern, the very act of looking, the simple act of asking the question, which path did you take, had forced the electron to abandon its ghostly wave-like nature and behave like a predictable, ordinary particle. It is as if the universe somehow knew it was being watched. The moment we measured its path, the wave of possibilities collapsed, the phantom chose a side, and all the other potential realities that would have contributed to the interference pattern simply evaporated. Remove the detector and the interference pattern comes back. Put it back and it's gone again. This became known as the observer effect, and it presented a philosophical crisis unlike any in the history of science. Observation was no longer a passive act of seeing what is there. Somehow the observer, the act of measurement itself, was an active participant in creating the reality it was measuring. This mind-shattering revelation cleaved the world of physics in two. On one side stood the Danish physicist Niels Bohr, the great patriarch of this new quantum mechanics. For Bohr and his colleagues in the Copenhagen interpretation, the lesson was clear, if deeply strange. An electron or any quantum entity does not have definite properties like position or path before it is measured. It exists in a state of pure potential, a mathematical abstraction known as a wave function that describes all its possibilities at once. The act of measurement is what forces this cloud of potential to collapse into one single concrete reality. Before you look, the electron really is not in any one place. It is a wave of probability. The universe, at its most fundamental level, is not deterministic, but probabilistic. To this, Albert Einstein, the man who had ignited the quantum revolution, balked with every fibre of his being. He could not accept that reality was so fuzzy, so dependent on our looking. He famously declared, "God does not play dice with the universe." He believed there must be a deeper hidden reality, hidden variables that we just hadn't discovered yet. The electron, he argued, must have a definite path all along. Our measurement simply reveals what was already there. For decades, these two titans of science argued, pushing each other to devise ever more clever thought experiments to expose the absurdity or the profundity of this new quantum world. Bohr's view seemed to suggest that reality is conjured into being by observation. Einstein fought for a universe that exists independently of us, solid and real whether we are looking or not. And so the mystery was drawn. We stood before a universe that behaved like a shy and cryptic spirit. When we aren't looking, it engages in impossible feats of phantom magic, with particles being in multiple places at once, behaving as waves. The moment we try to pin it down, to peek behind the curtain, the magic vanishes, and it presents to us a simple, mundane particle reality, as if to say, nothing to see here. The act of gaining information about the particle's past, its path through the slits, seemed to fundamentally alter its present behavior. This connection between knowledge and reality was the deep, unsettling core of the quantum puzzle. It raised a question that would simmer in the mind of a brilliant, imaginative physicist for years. A question that would take the paradox of the double slit and stretch it across the vastness of space and time. If our observation times here and now times can determine whether an electron behaved like a particle or a wave just a moment ago, what is the limit of this strange influence? What if the observation, the choice to look, was made long, after times the electron had already passed the slits and seemingly completed its journey? Could a choice made in the present truly reach back and rewrite a history that has already happened? This strange and intimate connection we share with the cosmos, this quantum pact, forces upon us an uncomfortable truth. Our glance matters. The simple act of observation, of asking which way did you go, collapses a universe of possibilities into a single concrete history. The ghost of a wave spread across all potential paths is exorcised, leaving behind the solid, lonely track of a particle. For half a century, this was the unsettling bedrock of the quantum world, a mystery codified by Bohr and his contemporaries. We were condemned to be disruptive witnesses, our very presence shaping the reality we sought to understand. But this fragile truce with the bizarre did not sit well with everyone. It certainly did not satisfy a mind that saw the universe not as a static stage, but as a grand, unfolding drama of information and existence. A mind that belonged to a poet of physics, a titan of thought named John Archibald Wheeler. Wheeler was a disciple of Niels Bohr, yet he possessed a uniquely American brand of intellectual audacity, a relentless curiosity that pushed him to test the very limits of his mentor's strangest ideas. He was a physicist who spoke in koans and drew cosmic conclusions from the sparest of equations, a man who had worked on the atomic bomb and would later coin the terms black hole and wormhole. He was not content to simply accept the observer effect as a brute fact of nature. He wanted to interrogate it, to push it, to break it if he could. He saw the standard double-slit experiment and felt it held a deeper, more profound secret, one that whispered of the strange relationship between time, choice, and reality itself. The question that haunted him was one of timing. Our decision to measure our choice to set up an experiment to find a particle seemed to tell the photon what to do times, before times it even began its journey. The setup dictated the outcome. But what if, Wheeler mused, we could be more cunning? What if we could stage an ambush? This was the genesis of one of the most provocative thought experiments in the history of science, a conceptual device so powerful it would send shivers down the spine of classical physics. He called it the delayed choice experiment. It begins as it must with the familiar apparatus. A single photon is fired towards a screen with two vertical slits. Beyond the slits, a vast emptiness waits. In Act 1, we learn that if you place detectors at each slit to see which path the photon takes, it dutifully behaves like a particle, picking one slit and one slit only. No interference pattern appears on the final screen. If you remove those detectors and let the photon fly unobserved, it acts like a magnificent wave passing through both slits at once, creating that signature pattern of light and dark bands. The choice, it seemed, was ours. But Wheeler added a diabolical twist, a modification so brilliant in its simplicity that it laid bare the deepest weirdness of the quantum realm. He imagined that we would let the photon make its journey in utter privacy. It leaves the emitter an indivisible quantum of light and hurtles towards the two slits. At this crucial moment, as it confronts this barrier, this fundamental choice of paths, we do nothing. We don't watch. We don't interfere. We allow it to exist in its purest state of quantum ambiguity, a shimmering cloud of probability. According to the orthodox interpretation, it is now a wave of potential, an ethereal ripple expanding through space, a wave that will pass through both openings simultaneously. It has, for all intents and purposes, committed to its wave-like nature. The event has happened. The photon is now past the barrier. Its journey through the slits is a fact, a moment relegated to the unchangeable past. It is now speeding towards the final detector screen at the far end of the chamber, carrying the information of its dual-path journey, ready to contribute to the growing interference pattern. But now, in the infinitesimally short span of time, times after times the photon has cleared the slits, but times before times it strikes its target, we make our move. This is Wheeler's ambush. At this last possible nanosecond, we make a choice. With the flick of a switch, a decision governed perhaps by the perfectly unpredictable decay of a radioactive atom, we can change the nature of the experiment itself. In one scenario, we do nothing. We leave the photographic plate in place, allowing the photon to land where it may. And just as Bohr predicted, over time, thousands of these photons, each left to its own devices, will build up the unmistakable interference pattern. Each one behaves as if it travelled through both slits, interfering with itself. This confirms its wave-like passage, a history that seems to have been written the moment it passed the barrier. But what if in that fleeting instant before impact our random trigger makes a different choice? What if it retracts the photographic plate entirely, and in its place with impossible speed it deploys a sophisticated system of lenses and 2B, separate highly sensitive photon detectors? One telescope is aimed precisely at the path a particle would have taken if it had come from the top slit. The other is aimed exclusively at the path from the bottom slit. Now we are no longer asking where did the photon land to see a pattern. We are asking a particle question, a which-way question. We are asking with brutal directness, which slit did you come from? The setup is now functionally identical to the version of the experiment with detectors placed right at the slits themselves. The only difference, the earth-shattering difference, is one of timing. Our decision to ask this question was made long after the photon had to have already decided how to navigate the slits, and here, in this conceptual crucible, reality itself seems to buckle. In every single instance that this version of the experiment is run, the outcome is unambiguous and utterly confounding. A photon will arrive. It will trigger one telescope and one telescope only. The other will remain dark. Click. A photon is registered as having come from the top slit. Another run. Click. A photon is registered as having come from the bottom. Another run. Click. Top. Never, not once, do both detectors fire, and never does neither fire. The photon, which a nanosecond ago was supposedly a wave that had passed through both slits, now provides a definitive answer that it travelled through only one, like a well-behaved little bullet. And if you run this version of the experiment thousands of times, the resulting data shows no interference whatsoever. The photons land in two distinct clumps, one aligned with each slit exactly as you would expect from simple particles. Let the weight of this settle upon you. The choice we made in the present, the decision to install the telescopes, appears to have reached back in time and altered a historical event. It seems to have forced the photon to choose a single definite path through the slits, even though that choice was made times after times it had already passed them. It is as if you arrived at the end of a long forking road, and by choosing to look back at the left fork, you retroactively force a traveller who passed the fork an hour ago to have taken that left path. It makes no sense. Causality, that sacred principle that a cause must always precede its effect, the very bedrock of our logical understanding of the universe, appears to be violated. The past, which we imagine to be a solid, immutable thing, a recorded history, suddenly seems fluid, negotiable, and terrifyingly responsive to our present actions. Wheeler's thought experiment was a gauntlet thrown down to the universe. He was directly questioning the very nature of a phenomenon. What does it mean for a photon to be a wave or be a particle? Does it possess these properties intrinsically? The delayed choice experiment screams no. It suggests that a photon is neither. It is something else entirely, something for which we have no word, a raw potentia that only crystallizes into a recognizable reality, into a past when we interrogate it. The history of the photon's journey through the slits does not seem to exist in any meaningful way until we measure it. It is not that we are discovering a pre-existing past. It is that our measurement itself helps to create that past. The questions we choose to ask, and crucially times we choose to ask them, become co-authors of the story of what happened. This concept was so radical, so profoundly unsettling, that it forced physicists to confront the deepest philosophical questions about their craft. What is a phenomenon if it is not a phenomenon until it is in times observed times phenomenon? Einstein had famously mocked quantum mechanics, asking if the moon is not there when nobody is looking at it. Wheeler's experiment sharpened the point of that question to an unbearable degree. It suggests that not only might the moon's presence depend on an observer, but its entire orbital history, the path it took to get where it is, might not be a settled fact until it is measured. Wheeler himself embraced this radical conclusion, proposing what he called the participatory universe. He argued that we are not merely spectators to the cosmic drama, we are active participants. Our observations, our questions, are the very mechanism by which the universe brings itself into being, transforming quantum uncertainty into classical historical fact. Imagine a cosmic game of 20 questions. The universe is the subject, but it has not chosen what it is. We, the observers, ask the questions. Are you a particle? The universe responds, yes. And in that moment it becomes a particle. Did you go through the left slit? The universe answers, yes. And in that instant, a history is forged where it went through the left slit. Had we asked a different question, are you a wave? The universe would have given a different answer, and a different history would have been solidified. Wheeler's point was that the reality was not hiding behind a curtain waiting to be revealed. The reality was constructed in the very act of questioning. The universe, in his poetic vision, is a vast self-referential system where meaning and existence are generated through the act of observation. This idea tears down the comfortable wall we erect between ourselves and the world out there. It suggests a level of interconnectedness that borders on the mystical. The classical view, the one that allows us to sleep at night, is that the past is fixed. The Big Bang happened. Dinosaurs roamed the earth. Your grandparents met. These events are over, locked away in the amber of time, unchangeable. Wheeler's quantum eraser, as it is sometimes called, suggests something far stranger. It implies that the past is just an illusion of certainty based on our macroscopic experience. At the fundamental quantum level, the past is an open book, a superposition of all possible histories until an observation is made that irrevocably selects one chapter and slams the book shut. The photon doesn't know we are going to look. It doesn't have a secret awareness of the future. The paradox is deeper than that. The problem lies in our very assumption that it had a single definite past before we looked. The delayed choice experiment forces us to abandon the intuitive idea of a little ball or a little ripple traveling through space. It compels us to think in terms of information. What information exists and where? Before the final measurement, the only information that exists is the potential for the photon to have gone through either or both slits. There is no definite fact of the matter. When we set up the telescopes, we are asking for which path information. The act of acquiring this information is what defines the event. If we get the information it came from the left slit, then that becomes the reality. If we instead perform a measurement that reveals interference, we are acquiring both paths information and times. That times becomes the reality. The history is not predetermined. The history is a consequence of the question we ask at the end of the story. For decades, this remained a thought experiment, a beautiful, terrifying paradox told by physicists around a chalkboard. It was a conceptual tool for sharpening the mind, a ghost story, to illustrate the profound break with classical intuition that quantum theory demanded. It was one thing to imagine a system that could cheat causality and rewrite history at the last possible second. It was one thing to speculate about a participatory universe where our present choices could reach back and define the past, but it existed only in the pristine, noise-free world of theory, a perfect and untouchable argument. The technologies required to actually perform such an experiment, to truly stage this ambush on a single quantum of light with the nanosecond timing required, seemed impossibly futuristic. But physics is not philosophy. Its ideas, no matter how wild, must eventually face the unforgiving crucible of experiment. The question lingered in the air, a cosmic dare. What if you could build it? What if you could actually pose this impossible question to the universe and force it to give you an answer? And so for decades, the paradox sat shimmering on the chalkboard. It was an elegant, terrifying ghost story, told with the language of mathematics. A thought experiment that pushed the logic of the quantum world to a breaking point from which it seemed there could be no return. Wheeler's cosmic scale interferometer, with its godlike observer, was a beautiful, untouchable abstraction, a philosophical torment designed to probe the very meaning of the past. But science cannot live on thought alone. An idea, no matter how profound, remains a ghost until it is summoned, until it is forced to confront the unforgiving verdict of physical reality. The question that haunted the quiet halls of physics departments was no longer times what if times, but times how asterisk. How could you possibly build a machine that could outrun light itself? How could you construct a question for the universe, and then in the final femtosecond change, that question after the messenger carrying the answer was already on its way? It seemed an impossible task, a challenge for a future generation. That future arrived sooner than anyone expected. It didn't arrive with galactic lenses and ancient quasars, not at first. It arrived in the hushed, climate-controlled darkness of the laboratory, a place of humming electronics, meticulously polished optics, and the faint electric scent of ozone. The 1,970 seconds and 80 seconds witnessed a quiet revolution, a mastery over the fabric of light and matter that was once pure fantasy. The laser, once a novelty, had been refined into an artist's brush, capable of painting with individual photons. Photomultipliers and avalanche photodiodes became our new eyes so exquisitely sensitive they could register the arrival of a single quantum of light, a whisper from the void. And most critically, electronics achieved a blistering supernatural speed. We forged switches such as Pockels cells that could be triggered in mere nanoseconds. These were not mere mechanical shutters, they were crystals whose very atomic structure could be twisted by an electric field, instantly changing the path light would take through them. A decision made and executed in a sliver of time, so small light itself could only travel a few feet. The toolkit was assembled, the stage was set. The ghost story was about to be put on trial. Imagine yourself there, standing in the heart of this apparatus. It's a cathedral of mirrors, crystals and wires sprawling across a steel table. Your sense of scale is warped. Distances that seem trivial to us, a few meters of air, become vast, uncrossable chasms for the photon at the heart of our story. The experiment begins with a pulse of precisely engineered light. A single solitary photon is born, a particle of pure energy, and sent on a journey into the heart of the machine. Its first encounter is with a half-silvered mirror, a pane of glass that is both a barrier and a gateway. This is the quantum world's great crossroads. Classical intuition screams that the photon must choose. It must bounce off taking the short path, or pass through taking the long path. It must commit. But as we've learned, the universe at this level does not deal in certainties, it deals in possibilities. The photon, obeying the strange laws of its existence, does both. Its wave function, the cloud of its potential realities, splits in two. One ghost of the photon travels down the short arm of the interferometer. Simultaneously, another ghost of that very same photon journeys down the long meandering arm. It is now in two places at once, a state of perfect, unresolved superposition. It is a wave rippling through the entire machine, exploring every possibility. Remember, at this precise moment in the photon's life, its journey past that first crucial fork in the road is an established fact. It is an event that has already happened. It lies in the photon's past, The two ghostly paths now race toward their destination, a point where they are destined to converge, and it is here at the end of the journey that we, the observers, prepare our cosmic ambush. At this final intersection sits our high-speed electronic switch, our Pockels cell. It is our instrument of delayed choice, the mechanism by which we will ask our final history-defining question. It is connected to a quantum random number generator, a device that ensures our decision is not predetermined, that it is as spontaneous and unpredictable as the universe itself. For billionths of a second, the system waits. The photon's divided essence, its wave of probability, is now inbound. It is committed to its journey. Its past is for all intents and purposes written. It has already navigated that first beam splitter as a wave, and only now, in the last nanosecond before the photon's ghost selves arrive, the random number generator makes its choice. An electrical signal traveling at nearly the speed of light fires. The fate of the experiment is sealed. In the first scenario, the switch remains off. The space at the intersection remains empty. The two probability waves, one from the short path and one from the long path, arrive and are allowed to simply overlap and continue on to two separate detectors. One detector is positioned to catch a photon from the short path. The other is positioned to catch a photon from the long path. We have chosen to ask the which path question. We have designed an experiment that can tell us definitively which route the photon took to get here. We fire another photon, and another, and another, thousands upon thousands of times. And the result? The detectors click in a random staccato. 50% of the photons are registered by the first detector. 50% are registered by the second. There is no pattern, no order, just a random spray of arrivals. By asking which way the photon traveled, the universe gives us an answer. It tells us the photon behaved like a decisive, resolute particle. It chose a single path. It picked a side. The wave with its ghostly superposition is gone. It is as if it never was. The photon in its history was a particle all along. But then we run the experiment again. This time everything is identical. The same laser, the same single photon. The same first beam splitter where the wave of potential is split in two. The photon's other self is once again traveling down both paths simultaneously. Its past is identical to what it was before. But this time, at the last possible nanosecond, the random number generator makes a different choice. The switch is thrown. In that infinitesimal moment, a second half-silvered mirror, our final beam splitter is activated and inserted into the intersection point. It is placed precisely where the two paths are set to converge. The ambush is sprung. This new mirror fundamentally changes the nature of our question. It erases the which path information. With this second mirror in place, the two incoming waves are forced to recombine. There is no longer a straight path to one detector or the other. Instead, the paths are merged. Now the photon's two ghostly selves can meet and interact. They can interfere with each other. If the wave crests from the two paths arrive together, they amplify each other. If a crest from one path meets a trough from another, they cancel out, creating a zone of absolute darkness where no photon will ever be found. We are no longer asking times which way times the photon went. We are now asking the universe to show us its wave-like nature. We let the experiment run. We send 1,000,000 photons into the machine. One by one they make their journey. One by one the choice is made at the last second, long after each photon has passed the first fork in the road. The results begin to accumulate on the screen, and what we see is breathtaking. It is impossible. The clicks from the detectors are no longer random. 100% of the photons arrive at one detector. The other detector, the one sitting in the path of destructive interference, remains utterly, completely silent. A perfect, beautiful interference pattern has emerged from the chaos. A pattern that could only times be created if each and every photon had traveled both paths at the same time, behaving as a single coherent wave. The act of inserting that final mirror, of changing our question at the end, reached back into time and reshaped the entire history of the photon's journey. The choice we made in the photon's future determined whether it behaved as a particle or as a wave in its own past. Let that sink in. This is not a metaphor. It is not a story. It is the cold, hard, empirically verified result. The experimental data confirmed in laboratories around the world with ever-increasing precision leaves no room for doubt. A decision you make times can fundamentally define what has already happened. The past, it turns out, is not a static monolith, a fixed and finished story. It is an open book, a shimmering cloud of possibilities, and our measurements, our questions, are the pen with which the final lines are written. We have caught the universe in the act of holding its breath, refusing to commit to a single history until the final act is played out. The photon doesn't know what our choice will be. It exists in a state of profound ambiguity. It is both a particle on a single path and a wave on all paths, all at once. This unresolved reality propagates forward through time until it encounters our measurement apparatus. Our choice to insert the mirror or not doesn't change a concrete past. Instead, it forces the universe to finally make a decision. It collapses that cloud of ambiguity into a single tangible history. If we ask a particle question, we get a particle history. If we ask a wave question, we get a wave history. We are not so much rewriting the past as we are times writing it times for the first time, sculpting the ghost of what was from the present moment. This is the central, staggering revelation of Wheeler's delayed choice, dragged from the realm of imagination into the stark light of the laboratory. It fundamentally overthrows our most deeply cherished intuitions about causality, about the relentless one-way arrow of time. We think of ourselves as passive observers, uncovering a pre-existing reality. We watch the movie of the cosmos as it unfolds, but these experiments show us something far more profound and far more unsettling. We are not merely the audience. We are in a very real sense the directors. The questions we choose to ask the universe play a crucial role in bringing its reality into being. The observer and the observed are locked in an inseparable time-spanning embrace. Our present actions don't just shape our future. They cast a long shadow backward, giving form and substance to the past itself. This is not science fiction. This is the world as it has been revealed to us. A world where history is an open verdict waiting for a question that has yet to be asked. The implications ripple outwards, shaking the foundations of our worldview. It forces us to reconsider the very nature of existence. What is an event before it is observed? Does the universe even possess a definite state when we are not looking? The laboratory experiments, for all their power, were just the beginning. They proved the principle in a controlled terrestrial environment over distances of a few meters and timescales of a few nanoseconds. But Wheeler's original vision was always grander. He dreamt of an experiment where the distances were not meters, but billions of light years. An interferometer where the laboratory was not a room, but the entire cosmos. And where the choice was not made by a random number generator, but by the chance alignment of galaxies and the gravitational pull of stars. Could this bizarre quantum effect, this temporal vertigo, truly stretch across the whole of cosmic history? Could a choice we make today in an observatory on Earth genuinely define the path a photon took from a distant quasar billions of years before our planet had even formed? The challenge was laid down once more. To take this unbelievable principle out of the lab and to test it against the canvas of the deep universe itself. And so the laboratory falls silent. The data flickers on the screen, a cold numerical testament to an idea that should have remained a philosopher's daydream. The choice made nanoseconds after the photon passed its crossroads has retroactively dictated the path it took. History, it seems, is not written in stone. It is written in pencil with an eraser held by the future. We are forced to stand at the edge of a precipice looking down into an abyss that separates our intuition from reality. Everything you have ever taken for granted, that the past is fixed, that events happen in a sequence independent of our looking, that the universe carries on, whether we are here to witness it or not, is now thrown into profound, terrifying doubt. This isn't merely a clever trick of light. It is a fundamental assault on the very concept of an objective world. For centuries, science has been a story of peeling back layers to reveal a solid mechanical core. A clockwork universe as Einstein so desperately wanted it to be governed by reliable local causes. An event here can only affect something over there by sending a signal, a physical influence that travels through the intervening space no faster than light. This principle, known as locality, is the bedrock of physics. Hand in hand with it is the idea of realism, the belief that objects have definite properties before we measure them. A moon exists and is a solid sphere even when no one is looking. A photon traveling through an interferometer must have a real, if hidden, property that makes it either a wave or a particle. It must know what it is, even if we don't. Together, these two pillars form what we call local realism. It is the scientific formalization of common sense, and Wheeler's delayed choice experiment takes a sledgehammer to both. If our future measurement determines the photon's past state, then its properties were never definite until we looked. Realism crumbles. And if that choice made here and now can instantaneously define a reality that existed back there moments ago, then some influence has violated the space between. Locality is breached. The universe is not a clockwork. It is a ghost story. This conclusion is so profoundly unsettling, so alien to our experience, that the first reaction from the scientific community was not acceptance. It was suspicion. A result this strange cannot be right. There must be a flaw, a loophole, a hidden door through which common sense can rush back in. And so began one of the most rigorous interrogations in modern science, a multi-generational effort to find an escape from the phantom. The hunt for loopholes is not an act of denial. It is the very heart of the scientific method. It is the process of a prosecutor trying to tear down their own case to ensure that what remains is the irrefutable truth. Perhaps some argued the detector making the final choice was not truly independent. Maybe it was somehow communicating with the photon's source, a subtle, undiscovered signal, creating a conspiracy to fool us into seeing this impossible result. This was the freedom of choice loophole, the idea that our experimental setup wasn't as random as we thought. The universe might have its thumb on the scale, or perhaps there was a failure in our detectors. Maybe our instruments are simply inefficient, missing certain photons in a way that just happens to perfectly mimic this bizarre quantum behavior. This is the detection loophole. It suggests we are not seeing the whole picture, but are instead being tricked by a carefully selected sample of data. For every baffling photon we register, maybe there are dozens we don't see that are behaving perfectly normally, restoring a comforting classical order to the cosmos. To close these doors, to eliminate any possibility of a hidden conspiracy, physicists had to devise even more ingenious, more mind-bending versions of Wheeler's original thought experiment. They needed to build a prison for reality with no possible escape. The first step was to take the idea of choice and information to its most extreme and delicate conclusion. They designed an apparatus known as the quantum eraser. Imagine again our photon having passed through the double slits. We now know that if we can acquire which path information, if we know which slit it went through, it behaves like a particle. If we have no such information, it behaves like a wave, creating the interference pattern. The quantum eraser adds a devilishly clever twist. It allows us to obtain that which path information, forcing the photon to commit to a particle-like history, but then at a later time it gives us the option to erase that information to render it unknowable. The experimental setup to achieve this is a masterpiece of complexity. It uses special crystals that can split a single photon into two, creating a pair of entangled twins. These are no ordinary photons. They are inextricably linked. Their fates are bound together by a quantum connection that transcends space. One photon, let's call it the signal photon, is sent towards our double slits and a final detector screen. Its entangled twin, the idler photon, travels a much longer path to a separate complex array of detectors. It is this idler photon that becomes our informant. By cleverly steering it with mirrors and beam splitters, we can measure it in a way that tells us which slit its twin, the signal photon, went through. The moment we do this, the moment we gain that knowledge, the signal photon, now far away, instantly loses its wave nature. On its detector screen, no interference pattern forms. It is as if a message travelled back in time to the signal photon as it passed the slits, telling it, "You are being watched, be a particle." But here is the miracle, the act of erasure. The choice is not yet final. The setup for the idler photon, our informant, has one last fork in the road. We can direct it to detectors that preserve the which path information. Or, at the very last moment, we can choose to send it into a device called a beam splitter, which scrambles its path irrevocably erasing any record of which slit its twin went through. We choose to forget what we once knew, and when we make that choice to erase the information, something impossible happens back at the other detector. The signal photons, whose histories should have already been sealed as particles, suddenly begin to form an interference pattern. The wave nature is resurrected from the dead. The act of erasing information in one location at one time reaches back and rewrites the physical history of another particle in another location at an earlier time. Let this sink in. We let the signal photon hit its final screen first. Its position is recorded, its journey is for all intents and purposes over. A moment later, miles away, we decide whether to keep or to erase the information carried by its twin. And that future choice determines the pattern that the past times photons created. It's as if we are not just observing the universe, we are co-authors of its history, editing the manuscript long after the ink should have dried. This entanglement-based experiment slammed the door on many loopholes. The choice was now separated by vast distances, ruling out any simple hidden signal between the components. The sophistication of the detectors made it nearly impossible to argue that we were being fooled by incomplete data, yet even this was not enough for the ultimate skeptics. There was still one final cosmic-sized loophole to consider: the freedom of choice problem. How could we be absolutely 100% certain that our choice of measurement made by a random number generator in a lab was truly random and independent of the photon's creation? Perhaps the entire system, from the laser that created the photon to the computer that made the choice, was part of a vast predetermined causal chain stretching back to the Big Bang, a kind of superdeterminism where true randomness doesn't exist and free will is an illusion. In such a universe, the photon and the detector were always destined to correlate, not because of quantum magic, but because their fates were written in the same ancient script. To challenge such a profound, almost theological objection, you cannot use a machine in a basement. You need a choice maker so far removed from your experiment, so ancient and so cosmically independent that no conceivable causal connection could exist. You need to let the universe itself make the choice for you. And so physicists looked to the heavens. They devised the ultimate version of Wheeler's experiment, one that would use the oldest light in the cosmos as its subject and entire galaxies as its laboratory equipment. They pointed their telescopes not at lasers but at quasars. Quasars, the incandescent, hyperluminous cores of infant galaxies powered by supermassive black holes feeding on cosmic chaos. They are the most distant, steadily shining objects we can see beacons from the dawn of time. The physicists found two ancient quasars burning brightly when the universe was less than half its current age. Their light began a journey towards Earth billions of years ago, long before our sun ignited, before our planet had even formed. This ancient light, travelling for eons across the expanding void, would be the photon source. But for the crucial fork in the road, the double slit, they needed something on a galactic scale. They found it halfway between the quasars and us. A massive galaxy cluster, a sprawling city of stars and dark matter so immense its gravity warps the very fabric of space-time around it. This cluster would act as a cosmic gravitational lens. As the light from a quasar behind it passed by space-time itself, would offer the light two distinct paths around the gravitational behemoth. One path curving around the left side of the cluster, the other around the right. These two gravitationally lensed paths are the universe's own double-slit experiment. For 6 billion years, a single photon from that quasar has been in a state of superposition, simultaneously travelling both paths around the intervening galaxy cluster. Its nature, its history, suspended in an indeterminate quantum fog. It is both a particle that took a single path and a wave that took both all at once. And it has remained in this state of ambiguity while continents drifted on Earth, while empires rose and fell, while our own species evolved from primates to astronomers. Now, in the final fraction of a second of this 6 billion year journey, the light enters a telescope on Earth, and it is here that we make the delayed choice. In our observatory, we can point the telescope directly at the photon to see which of the two paths it arrived from. This is the particle measurement. We acquire the which path information, and in doing so, we force that photon to have chosen a single definite path around that galaxy cluster billions of years ago. Our observation in the present crystallizes a moment in the distant past, or we can make the other choice. We can place a beam splitter at the telescope's focus, erasing the path information. This setup recombines the light from both paths, allowing us to check for interference. The wave measurement. If a wave pattern appears, it is proof that the single photon did not choose a path. It must have traveled both routes around that galaxy cluster, simultaneously acting as a coherent wave stretched across hundreds of thousands of light years. And our choice to look for a wave today now would be what times made times it behave that way 6 billion years ago. To ensure the choice was truly free and independent, the decision of which measurement to make was triggered by a random number generator that observed quantum fluctuations from a completely different, unrelated quasar located in the opposite direction in the sky. The light from this choice-making quasar was hundreds of millions of years old. There is simply no way, under any known law of physics, that the photon being measured could have had any causal connection to the distant quantum event that was deciding its fate. One signal would have had to travel for 6 billion years, the other for hundreds of millions, and they only meet in our detector at the last possible instant. The universe had provided the perfect loophole-free test. The experiment was run, the data was collected, and the result was unambiguous. When the astronomers chose to look for which path the photon took, they found it had always taken one specific path. When they chose to erase that information and look for interference, the pattern was there, clear as day, proof that each photon had traveled both paths at once. Every time, without fail, the cosmos itself had spoken, and it confirmed Wheeler's most outlandish prediction. There are no more loopholes, there are no more classical escapes. We are left here in the quiet of the observatory, staring at numbers that feel like scripture from an alien god. We are face to face with the unavoidable conclusion that our measurements today are reaching back across cosmic epochs to participate in the creation of ancient history. The very idea of a past that exists separate from the present collapses. The universe does not have a single objective story. It is a vast collection of possibilities, a quantum fog, and it is only where observation intersects with reality that a concrete history is precipitated from the mist. We have hunted the ghost in the machine to the edge of the cosmos, and in the end, we have found that the ghost is us. Our consciousness, or at least the act of measurement it requires, is not a passive observer of a pre-existing movie. We are the editors, and perhaps even the directors of a film whose beginning is written at its end. But if that is true, if the scaffolding of causality can be so easily dismantled, what does that say about the nature of time itself? What does it mean for our place in this participatory universe, and what other even stranger realities might be waiting for us to simply make a choice, and in doing so, call them into being, and so we stand at the precipice of an impossible conclusion. The photon, that single pilgrim of light, has completed its journey. It has traversed the vast, cold emptiness of the interferometer, and our choice, our simple human decision made long after, seems to have dictated a history that had already transpired. We find ourselves staring into the abyss of a temporal paradox, a cosmic crime scene where the effect appears to precede the cause. How can this be? How can an action in the present sculpt the unchangeable stone of the past? The question reverberates through the halls of physics, challenging the very foundation of what we call reality. It is a question so profound that it has fractured the scientific community, pitting titans of thought against one another in a battle for the soul of the cosmos. The evidence is undeniable, yet the explanation remains elusive, a ghost we can see but cannot grasp. For the old guard, the architects of the quantum revolution, the followers of the venerable Copenhagen interpretation, this entire dilemma is a phantom of our own making. Niels Bohr, its primary author, would have met our paradox with a stern philosophical rebuttal. He would argue that we are asking a forbidden question. We are trying to impose our clumsy classical intuition onto a realm where such intuition has no meaning, no purchase. For Bohr, there is no independently existing reality for the photon's journey. There is no path for it to have taken until a measurement is made. The quantum world is a misty, indeterminate realm of potential, a ghostly superposition of all possibilities at once. It only snaps into a concrete knowable state when it interacts with a large-scale classical measuring device, our detector. The universe in this view does not possess a story about the photon until we force it to tell one. When we set up the experiment to detect which path information we are asking the universe, the question, "Are you a particle?" the entire apparatus from the photon's emission to its detection conspires to answer that specific question, and the photon obliges. It behaves as a particle yielding a definite path. When we set up the experiment to detect interference, we are asking a different question, "Are you a wave?" And again, the entire system from beginning to end reconfigures itself to provide the answer to that times question. The photon behaves as a wave, creating an interference pattern. The delayed choice doesn't rewrite a past event. According to the Copenhagen view, it redefines the time's entire phenomenon asterisk. There was no particle history to erase or wave history to invent. There was only a quantum cloud of possibility, a mathematical abstraction. Our choice of question in the present determines which property of that abstraction becomes real, not just now, but for its entire lifespan. It's a stark, almost severe perspective. It draws a hard line in the sand between the quantum and classical worlds, a boundary that Bohr called the Heisenberg cut. Below that cut, there are no particles or waves, only potentialities. Above it, in our world, there are only definite results. The past isn't being rewritten. It's being written for the first time, and the ink is our act of observation. This interpretation offers a way out of the paradox, but at a tremendous cost. It forces us to abandon the deeply held belief that there is a real objective world ticking away out there, independent of our interaction with it. It suggests the moon is not truly there when no one is looking, a proposition that even made Einstein deeply uncomfortable. It solves the puzzle by declaring the puzzle itself an illusion, a linguistic error born from our classical prejudice. Many physicists found this answer profoundly unsatisfying, a philosophical sleight of hand, rather than a physical explanation. It felt less like a discovery and more like a surrender. But from this dissatisfaction from the intellectual ashes of this debate, a far more radical, far more unsettling possibility emerged. It came from the mind of a young, audacious physicist named Hugh Everett III, who dared to ask, what if the quantum math is telling us the literal truth? What if the photon really does explore both paths simultaneously? What if, when we make our measurement, the universe doesn't choose one outcome? What if instead it chooses all times of them? This is the genesis of the many worlds interpretation, an idea so vast, so mind-bending, it stretches the limits of human imagination. Everett proposed that the wave function, that mathematical description of all possibilities, never truly collapses. It simply branches. Every time a quantum measurement is made, reality itself splits. The universe cleaves into multiple parallel copies of itself, each one containing a different outcome of the measurement. These universes are not hypothetical. They are, in this view, all equally real. They coexist, layered on top of one another forever, unable to interact or communicate. Let's return to our photon at the final beam splitter. In the moments before our choice, the universe is in a state of superposition. There is a reality where the photon is a wave, and a reality where it is a particle, both contained within a single unified quantum state. When we make our decision to insert the final screen or not, we are not choosing the photon's past, we are choosing our own future. We are choosing which branch of the universal wave function we will follow. If you choose to look for the interference pattern, you find yourself on a branch of reality where the photon has behaved as a wave all along. Simultaneously, a copy of you in a universe that has just split off from your own has chosen to look for the which path information. And in times their times reality, on times their times branch, they find a photon that has behaved as a discrete particle all along. There is no paradox. There is no rewriting of history. There is only the great bifurcation. One history for one branch of reality, a different history for the other. Both are completely consistent within their own timeline. The delayed choice experiment, seen through the many worlds lens, is not a temporal enigma but a cosmic sorting mechanism. Our choice acts as a filter determining which version of history we become consciously aware of, which cosmic storyline we inhabit. The other histories, the paths not taken, are not erased. They are simply happening elsewhere to other versions of us. This vision is at once terrifying and sublime. It paints a picture of a multiverse, a block of infinite realities, where every quantum possibility is realized somewhere. It saves causality and objective reality, but it does so by populating the cosmos with an uncountable number of ghost worlds, each one containing a version of you living out the consequences of every quantum coin flip that has ever occurred. It is an idea of breathtaking scope, an extravagant solution that solves the paradox by embracing an infinite unseen reality. For many, the cost of these unseen worlds is too high a price to pay an unprovable, unfalsifiable fantasy. But for others, it is the only interpretation that takes the quantum mathematics at its word, following its logic to its ultimate staggering conclusion. Yet another interpretation plunges even deeper into the temporal abyss, suggesting a mechanism so strange it borders on mysticism, yet is built on the rigorous foundation of quantum field theory. This is the transactional interpretation proposed by John Cramer. It dares to suggest that the communication between the past and the future is not a paradox, but a fundamental feature of reality. It envisions every quantum event not as a one-way street, but as a two-way conversation happening across time itself. Imagine our photon being emitted from its source. According to Cramer, the emitter doesn't just send a wave forward in time. This is the offer wave rippling through space-time, exploring all possible paths, carrying the blueprint of what times could times be. This offer wave travels to the future, to the location of our detectors. When a detector is poised to absorb a photon, it feels this incoming offer wave, and in response it sends back its own wave. This is the confirmation wave, and it travels times backward, times in time, from the future detector back to the past emitter. It is a celestial handshake, a negotiation between the future and the past. The offer wave says, "I am here, these are my possibilities." The confirmation wave replies, "I accept your offer, this is the path you will take." The transaction is completed only when the offer and confirmation waves meet and reinforce one another along a single specific path through space-time. The physical photon, the particle of light we actually see, only travels along this consummated path. All other potential paths where the handshake was not completed simply fade away. In this extraordinary picture, our delayed choice is no longer a mystery. When we remove the final beam splitter, the detectors at the end of the two paths are the potential absorbers. They send their confirmation waves backward in time. The confirmation wave from whichever detector fires completes the transaction, and a single definite particle history is established. But when we insert the final beam splitter, the setup changes. The detectors are now placed times after times the point of recombination. It is these times detectors that send confirmation waves back in time. Because their existence depends on the two paths interfering, the resulting transaction is one that establishes a wave history. The handshake that is completed is one where the offer wave from the emitter is confirmed to have traveled both paths simultaneously. The past in this view is not a fixed monument. It is an ongoing negotiation, a dynamic interplay of waves moving both forward and backward through the river of time. Our choice in the present influences which confirmation waves are sent back, and thus which transaction is finalized, which history becomes real. It doesn't violate causality in the classical sense. You cannot send a signal back in time to change a past you remember. The entire transaction happens outside of time, as we perceive it in a timeless quantum realm where past and future are intertwined. It is a radical, beautiful, and deeply strange idea. It suggests that the universe is constantly whispering to its past, that the future is always leaving echoes for its younger self to find. The transaction is a story written by both its beginning and its end, a cosmic narrative co-authored by emission and absorption. And then there is the view of the man who started it all, John Archibald Wheeler. As he aged, Wheeler became increasingly philosophical, convinced that the puzzles of quantum mechanics pointed to something even deeper about the nature of existence itself. He began to champion an idea he summarized in the phrase, "it from bit." This is the proposition that the universe at its most fundamental level is not made of matter or energy, but of information. That every particle, every field, every star, and every galaxy is ultimately derived from the answers to yes or no questions, from bits of information registered by acts of observation. In Wheeler's participatory universe, reality is not a pre-existing stage on which events unfold. Instead, reality is something that is brought into being through the very act of asking questions, of making measurements. The universe he imagined is like a vast cosmic game of 20 questions. It doesn't have an answer in mind until you start probing it. When we perform the delayed choice experiment, we are asking it a question. Did the photon travel one path or both? The universe, Wheeler argued, was under no obligation to have an answer before the question was posed, even if the asking happens billions of years after the event took place. The photon's journey is not a physical history until it is registered. Until then, it is pure information, pure potential. Our choice of how to measure it provides the question that forces this potential to resolve into a concrete bit of information, and it. From this perspective, the past is not being rewritten. The past had no definite form to begin with. It existed only as an unrealized informational cloud. Our observation in the present reaches back and gives that cloud a tangible shape. We are not just passive observers of a cosmic drama. We are active participants in its creation. Our measurements, our very consciousness, might be the mechanism by which the universe's quantum potential becomes classically real. It is a profound and humbling thought that we, the transient inhabitants of a small planet, are somehow involved in cementing the history of the cosmos itself. One observation, one bit of information at a time. So, where does this clash of titans leave us? Copenhagen, many worlds, the transactional view, Wheeler's it from bit. Each offers a different path out of the paradox, a different map of reality, and yet a common thread runs through them all, a single revolutionary conclusion that serves as the resolution to our cosmic mystery. The central conflict can be settled not by choosing one interpretation over another, but by accepting the radical truth they all in their own way reveal. We cannot physically alter history. We cannot send a message to our past selves, win the lottery, or prevent a tragedy. The classical past, the one we remember, the one written in our history books and carved into our monuments, is fixed. But the quantum past is a different beast entirely. The experiment forces us, with a logic as cold and sharp as a diamond, to abandon our most cherished assumption that the past is a single concrete settled thing. It is not. At the quantum level, the past of a particle is not a determined reality. It is a ghost, a whisper, a quantum potentiality. It is a superposition of all possible histories, all possible paths existing simultaneously in a state of unresolved tension. It remains in this state of limbo, this fog of maybes, until a measurement, an observation, an interaction with the present forces it to choose. Our present observation does not times change times the past. It times creates times the past. It reaches back into that haze of possibilities and collapses it, crystallizes it into a single definite state. The history of that photon, whether it was a wave or a particle, was not written billions of years ago when it began its journey. It was written just now when it landed on your detector. We are not merely reading the history book of the universe. We are, in a very real sense, helping to write the final draft. This is the profound legacy of Wheeler's experiment. It transforms our understanding of time and existence. The past is not a solid foundation upon which the present is built. Instead, the past and present are locked in a strange quantum embrace, each one giving definition to the other. The present moment becomes a chisel carving details into a past that was until this instant a block of unformed marble. We are forced to accept a universe far stranger than we ever imagined, one where what has happened is inextricably linked to what is happening now. And this realization opens up an even more unsettling vista of questions. If our observations can define the microscopic past, what does that imply for the grand sweep of cosmic history? Could the vast unfolding story of the universe itself, from the Big Bang to the present day, also be contingent, waiting for a fast, conscious observer to give it meaning, to make it real? We are moving beyond the realm of simple experiments and into the very heart of cosmology and existence itself. Our journey together began in a world of comfortable certainty, a cosmos imagined by Newton and Einstein as a grand, predictable clockwork. It was a universe where things were what they were, where a particle was a particle, a wave was a wave, and the past was a fixed, unalterable country from which no message could ever be returned. We have walked a long and winding path from that solid shore, venturing out into the ghostly waters of the quantum realm. We followed a single photon on its lonely pilgrimage through the twin slits, watching it perform an impossible feat of being in two places at once, only to find that our simple act of looking, of asking which way did you go, collapsed its ethereal potential into a single concrete fact. That initial paradox, the wave-particle duality, was the first tremor that shook the foundations of our understanding. It was the whisper that reality was far stranger, far more fluid, and far more participatory than we could have ever dared to imagine. It suggested that the universe was not a film we were merely watching, but a play in which our own observation was a critical part of the script. But even that revolutionary idea held a fragile comfort, the comfort of linear time. We assumed our choices, our measurements, our questions could only affect the present and the future. The past, we believed, was safe, locked away behind the inviolable laws of causality. Then came John Archibald Wheeler, a physicist with the soul of a poet who dared to ask the most unsettling question of all. What if you could choose times after times the event had already happened? What if you could reach back across the chasm of time and retroactively decide the nature of the past? This was the genesis of the delayed choice experiment, an idea so radical it bordered on science fiction. It took the already baffling nature of quantum mechanics and twisted it into a temporal knot. We travelled with his thought experiment from the laboratory bench to the vast, cold emptiness between galaxies, watching a photon launched billions of years ago from a distant quasar. We saw its path bent by the immense gravity of a foreground galaxy, creating two possible routes to our telescope on Earth. For millennia, that single quantum of light travelled as a superposition, a ghostly wave of pure potential, exploring both cosmic highways simultaneously. And then, at the very last moment, in the final femtosecond of its epic voyage, our choice to install a detector or a screen would reach back through those billions of years of history. Our decision made in the here and now appeared to dictate whether that photon had travelled a single definite path or both paths at once, an eon before we even existed. Here, at the culmination of our exploration, we must stand and confront the staggering implications of this fact. The Wheeler delayed choice experiment is not a mere curiosity, a quirky footnote in the annals of physics. It is a profound and unyielding challenge to the very bedrock of our perception. It forces us to abandon the comforting notion of a single objective pre-existing history. The universe, it seems, does not write its story in permanent ink. Instead, it appears to write in pencil, leaving the final version of the past contingent on the questions we choose to ask in the present. This concept is so deeply counterintuitive, so violently at odds with our everyday experience, that it feels like a logical impossibility. Yet experiment after experiment conducted with ever-increasing precision has confirmed Wheeler's startling prediction. Reality at its most fundamental level refuses to commit. It remains a shimmering haze of possibilities, a quantum fog until an act of measurement, an interaction with a conscious observer, or even a simple inanimate detector forces its hand. And that act of measurement doesn't just shape the future. It appears to crystallize a specific version of the past from a menu of could-have-beens. What does this truly mean for our understanding of existence? It shatters the classical view of the observer as a passive bystander. We are not separate from the universe we study. We are inextricably woven into its fabric. Wheeler himself coined a powerful term for this, the participatory universe. In this model, the cosmos is not a finished product that we discover piece by piece. It is an ongoing act of creation, and we are in a very real sense co-creators. Our questions, our measurements, the very act of our conscious engagement with the world are what help to transform uncertain quantum potential into concrete classical reality. Think of it as a cosmic game of 20 questions. The universe holds all possible answers, all potential histories, in a state of superposition. It is only by asking a question, by setting up an experiment, by making a measurement, that we compel it to provide a definite answer, and in doing so we participate in the construction of the reality we perceive. The past of that photon wasn't fuzzy or unknown until we measured it. According to this radical interpretation, it simply had no definite history at all. It existed as a pure what if until our present action provided the what is. This idea propels us from the realm of physics into the deepest chasms of philosophy. For millennia, thinkers have debated the nature of time. Is it a river flowing inexorably in one direction, or is it more like a landscape, a block universe where past, present, and future all exist simultaneously, and our consciousness merely illuminates one moment at a time? Wheeler's experiment lends a strange new weight to the latter view, but with a disturbing twist. If the future can influence the past, then the very concepts of before and after lose their absolute meaning. Causality, the sacred law that an effect cannot precede its cause, is not violated in the classical sense. No information travels backwards in time to warn you of a future event. But the times definition, times of past events, their very nature, seems to be held in abeyance pending future circumstances. It's as if the universe waits to see how the story ends before it decides how it began. This is a reality where the script is being written and edited in real time, where the final act can retroactively change the character motivations in the first. The implications ripple outward, touching everything we hold to be fundamental. Consider the concept of information. Wheeler, in his later years, became obsessed with the idea he called it from bit. He proposed that the physical world, the it, might ultimately be reducible not to matter or energy, but to information, to binary yes or no questions, the bits. In this light, the delayed choice experiment becomes a stunning demonstration of this principle. The universe doesn't seem to care about the physical path of the photon. What matters is the information we gain. If we acquire which path information, the photon behaves like a particle. If we erase that information, or choose not to acquire it, it behaves like a wave. The physical reality of the photon's journey seems to be a direct consequence of the informational state of the system, a system that includes us, the final observers. Perhaps the universe is not so much a collection of things as it is a colossal information processing system, a quantum computer of unimaginable scale and complexity. And perhaps what we call reality is simply the output of its ongoing calculation, an output that is constantly being updated based on new inputs, our measurements. This radical reimagining of the cosmos is not merely a philosophical indulgence, it is the driving force behind some of the most advanced scientific research today. The very quantum weirdness that Wheeler's experiment illuminates is being harnessed to build the technologies of the future. Quantum computers, for instance, rely on the principles of superposition and entanglement to perform calculations that are impossible for even the most powerful supercomputers. Their ability to explore a vast landscape of potential solutions simultaneously is a direct echo of that ancient photon exploring both cosmic paths at once. The delayed choice principle, the idea that a later measurement can define an earlier state, is not just a paradox to be debated, it is a feature to be exploited, a powerful tool in the design of quantum algorithms. The quest to build a quantum internet, a network that could transmit information with perfect security, relies on the same ghostly connections between particles that underpin this experiment. By understanding how observation and information shape reality, we are learning to speak the universe's native language and with it to write our own technological future. Furthermore, the delayed choice experiment continues to serve as a crucial touchstone in the grandest quest of all the search for a unified theory of everything. Physics is currently split between two remarkably successful but fundamentally incompatible theories. Einstein's general relativity beautifully describes the large-scale universe of gravity, planets, and galaxies, a world of smooth, continuous space-time. Quantum mechanics, on the other hand, describes the small-scale world of particles and forces, a world of discrete packets, probabilities, and observer effects. For decades, the greatest minds in physics have struggled to reconcile these two views, to find a single, elegant theory, often called quantum gravity, that can describe both the dance of galaxies and the flicker of a single electron. The delayed choice experiment, particularly its cosmological version, operates at the precise, tantalizing intersection of these two domains. It involves a quantum phenomenon, a single photon in superposition, unfolding on a cosmological stage shaped by Einstein's gravity. Any future theory of quantum gravity must be able to explain from first principles how a measurement made on Earth today can define a history that was sculpted by the gravitational lensing of a galaxy billions of years ago. It must have something profound to say about the nature of time, the role of the observer, and the fabric of space-time itself. Wheeler's puzzle is not just for quantum physicists. It is a challenge to the cosmologists of tomorrow. New and even more mind-bending versions of the experiment are being proposed and tested. The quantum eraser variation, which we briefly touched upon, adds another layer of complexity, showing that we can not only choose to reveal the particle nature of a photon, but we can then times erase times that information and restore its wave-like behavior, as if the choice had never been made. Scientists are now exploring how these principles might apply to more complex systems, even to the boundary between the quantum and classical worlds. Could a macroscopic object under the right conditions be placed in a state where its past is undefined? Could the arrow of time itself be a local emergent property rather than a fundamental law of the universe? These are the questions that keep physicists awake at night, questions born directly from the legacy of Wheeler's audacious thought experiment. They are pushing the boundaries of what is knowable, forcing us to confront the possibility that the universe may be fundamentally non-local, interconnected in ways that defy our classical intuition, linking the far-flung past with immediate present. So where does this leave us, you and I? As we stand at the end of this journey, we are left with a universe that is profoundly more mysterious, more magical, and more deeply interconnected than we ever knew. We are left with the humbling realization that the solid ground beneath our feet is a construct, a consensus reality pulled from a sea of infinite potential. The delayed choice experiment does not provide easy answers. Instead, it presents us with a sublime and terrifying choice of interpretations. Perhaps we live in a many-worlds multiverse, where every quantum measurement splits the universe into parallel branches, each representing a different outcome, and our choice simply determines which branch of history we experience. Or perhaps consciousness itself is the key, the one element in the universe capable of collapsing the wave function and conjuring reality into being. Or perhaps most strangely of all, the universe simply does not possess definite properties until they are measured, and our concept of a past is a human illusion, a story we tell ourselves to make sense of a reality that is eternally, ceaselessly in the present tense of becoming. We are forced to trade the cold comfort of a clockwork cosmos for the exhilarating uncertainty of a participatory one. We are no longer mere spectators to the grand cosmic drama. We are actors on the stage, and our choices, our questions have consequences that ripple not just into the future, but deep into the heart of the past. The legacy of John Wheeler's thought experiment is this enduring sense of wonder. It reminds us that science is not just a collection of facts, but a continuous process of inquiry, a courageous journey into the unknown. It teaches us that the deepest truths about the universe are not always whispered. Sometimes they scream, and what they scream is that reality is not what it seems. The quest to understand is far from over. The final pages of the cosmic script have not yet been written, and we, armed with our curiosity, our telescopes, and our theories, have been handed the pen. The universe is waiting patiently for the next question we dare to ask, ready to reveal another layer of its magnificent, unfathomable secret.